In this video, we will introduce Kirchhoffs' current law, which is one of the fundamental laws of circuit analysis. Quite often, you'll see it referred to as KCL for obvious reasons. Let's start the explanation by looking at this strange circuit that I've drawn. The point here is a node in the circuit, and the funny green stuff is what we'll call the rest of the circuit. For Kirchhoffs' current law, we don't even care what the rest of the circuit is. All we care about is that it's connected to the node through multiple connections. Kirchhoffs' current law works this way. I1 plus I2 plus I3 plus I4 plus I5 is equal to 0. In words, the sum of all the currents entering a node is equal to 0. Now, some of you may look at this and say, wait, how can you have the sum of all currents entering the node be 0? Well, what it means is that some of these currents will be negative, and the way we've drawn the arrows won't show how all the currents are going to flow. In other words, some of the currents will flow out of the node in the direction opposite the arrows. Conceptually, what this means is that current, which is flowing charge, flowing into the node is the same as the current, which is flowing out of the node, which basically means that as much charge flows in as flows out. So I don't have charge accumulating at the node. And so that's basically what we're saying with KCL. Another way of writing KCL would be the following. Suppose I have drawn some of the currents in the opposite direction. So for example, I've drawn I1 and I2 as flowing into the node, but I3 is flowing out, I4 is flowing in, I5 is flowing out. I can write KCL for this situation as I1 plus I2 plus I4 is equal to I3 plus I5. In words, the sum of the currents entering the node is equal to the sum of the currents leaving the node. I tend to prefer doing it this way rather than saying the sum of all the currents entering the node is 0, because it makes sense to me that the total current flowing in must be the same as the total current leaving. So with that as an introduction, let's actually do an example. I have drawn a circuit that represents 4 light bulbs connected in such a way that they will all be lighted at the same time. The light bulbs are represented by resistors. Those are the squiggly lines. For your information, the first light bulb is a 100-watt light bulb, then 2 60-watt light bulbs, and 1 40-watt light bulb. With Ohm's law, you should be able to convince yourself that, given the voltage and the values for the resistances which model the light bulbs, we do indeed have 100-watt, 2 60-watt, and 1 40-watt bulbs. I want to compute the total current coming out of the source. One reason why I might want to do this is perhaps I want to know how much current it's going to take to light these light bulbs. I need to know this, for example, to be sure that I won't put too many light bulbs on one circuit, and so I won't trip a circuit breaker. I'll label the current coming out of the source as I, the current going through the 100-watt bulb as I1, the current going through the first 60-watt bulb as I2, the current going through the second 60-watt bulb as I3, and the current going through the 40-watt bulb as I4. And again, I want to find out what the total current is. So I can write down KCL, which says that the total current flowing into the node is equal to I1 plus I2 plus I3 plus I4. Now, at this point, I'd like to take a bit of a digression, because I've discovered that this particular point can be rather confusing, and it's one of the big misconceptions that students have. Sometimes students will think that the node would be wherever I join wires, and my previous picture to introduce KCL might reinforce that misconception. But a node is anywhere I can get to by following a wire. So as I draw here, I'm actually drawing a green line that encloses all of one node. So this part that I've drawn in green is all one node. And the way I can tell that is I can get from any point, say this point here, over to some other point, say this point here, by just following a wire. There are no components on my path from here to here. And if you look at the way I've drawn this green outline, there are no components on the path between any part of the wire in the green outline to any other part of the wire in the green outline. So this green thing is a node. And because it's a node, I can apply Kirchhoffs' current law to it, which gives me the equation that we have. Similarly, the part that I'm outlining in red is also all one node. This is important to me because the voltage source is going to make sure that the voltage between the green node and the red node is 120 volts. The voltages across all the resistors are 120 volts. Since I now know these voltages, I've got a voltage and I've got a resistance. If I know the voltage across this resistor and I know its resistance, I can use Ohm's law to get its current. So I1 will be 120 volts over 144 ohms, which turns out to be 0.83 amps. I2 will be 120 volts over 240 ohms, which is 0.5 amps. I3 will be the same, 120 volts over 240 ohms, which is 0.5 amps. And I4 will be 120 volts over 360 ohms, which is 0.33 amps. So if I plug all of these numbers in and solve for I get that I is equal to 0.83 amps from I1 plus 0.5 amps plus 0.5 amps plus 0.33 amps, which is 2.16 amps. Okay, so what this says is that the voltage source, in order to keep 120 volts across each of the light bulbs, will have to put out a total of 2.16 amps. Before we end, I'd like to address two common misconceptions. First, the currents leaving the node, that is I1 through I4, are not all the same. Some novice circuit analysts assume that since we have the same voltage across these four parallel resistors, that the current splits into equal currents through each resistor. However, that's not true. The current through a resistor will depend on the value of the resistor. That's why I1 is the largest current. The 144 ohm resistor is the smallest resistor. That's why I4 is the smallest current. The 360 ohm resistor is the largest. Another common misconception is that current always takes the path of least resistance. If that were true, all of the current would flow through the 144 ohm resistor. Now, it's true that more current flows through the 144 ohm resistor, but not all of it will flow through the path of least resistance. So, this concludes the video on Kirchhoffs' current law, and I hope you've enjoyed it.